All right, everybody. We have our next talk right here. This is Omar Minawi. You got it. He's going to be giving a talk on client-side JavaScript from your nightmares. I've already seen this talk, but I'm going to see it again because it was really good, and I hope you guys enjoy it. Let's give it up for Omar.
Awesome. Thank you so much for the super kind introduction. Hi, everyone. My name's Omar, and I'm really excited to share with you my talk where we're going to talk about some client-side JavaScript that showed up in my nightmares, and now I want it to show up in yours too. This is actually my first time in Knoxville and first B-Sides. It's been a great week, and I'm really excited to share this with you. Okay, so before we begin, a little about me. I'm an application security engineer at Cisco Meraki. I help empower developers to write secure code, and I do this by leading projects to assess services and applications in the company. I've authored multiple publications at the ACM MSwim conference, where I've published papers proposing machine learning-based intrusion detection systems for drones and controller area networks. So if you're interested about ML-based IDSs or CAN bus stuff, I'd love to chat. I'm doing my master's in CS at Georgia Tech, and I like snowboarding and cars, specifically Porsches. So in this presentation, I have a really interesting exploit chain I'm going to be walking through. And this whole presentation was inspired by a real attack chain. And what we'll do is we'll start light. We'll start off with an attack demo, and then we'll dive into the attack vectors. We'll talk about some web exploit research, and then wrap it all together with some defense in depth and some mitigations. All right. So in this whole presentation, I'm going to be talking a lot about cross-site scripting. And for those who don't know, cross-site scripting is a common issue. It's grouped in the injection family. And with this, this occurs on applications when user input is accepted and it's not encoded or sanitized upon input also, and then the application takes it, does some processing, and returns it to the user, and it doesn't encode or sanitize the input upon output as well. And this can result in some really funky functionality, as we'll see in this presentation. And in terms of impact, the impact for these attacks really depends on, for example, if the application has a database, which pages are impacted, and which functionality you're targeting. And so the impact can really range. So in this presentation, we're going to talk about corp.com. And corp.com has two sites, a portal and a shop. And what's interesting is we found that corp.com's portal site was vulnerable to a reflected cross-site scripting attack in the queue parameter. The queue parameter in the search method was injectable. And what this means is if someone sends you a link like this and you click it, you're going to get a pop-up like this because the JavaScript was accepted by the user into the page. The application didn't process it correctly. It didn't encode it or sanitize it upon output when it returned it to the user. And so you get, this is a very basic payload we've all learned when we first were taught about cross-site scripting on Portswigger's Academy. But what's interesting is the actual attack was nowhere near this simple. What happened is using JavaScript, the attacker set a cookie called special cookie. And what they did, and this cookie was scoped to all of corp.com subdomains. And what happened was the cookie had some strange payload, and then the attacker redirected the user to the shopping site. And then, so for example, we click on this link, we go to the portal site, and then we get redirected to the shopping site, and all of a sudden our cookies get dumped. And we're like, how did this happen? I was on the shopping site, one trust domain, then I got transferred to, or I was on the portal, then I got transferred to the shopping site, and then all my cookies got dumped. And this is really interesting. And if we take some time and we open up the cookie jar and we really see what's going on, that first cookie that was set in the initial reflected cross-site scripting vector went ahead and set special cookie with some really strange content. And this highlights the rest of the investigation that we're going to go through together. So looking at a deep dive, I want to introduce you to one of the main stars of this presentation called Script 1. Script 1 is a script that the shopping site uses for analytics. It's business as usual. And script 1 has some very interesting functionality where script 1 is once the shopping site loads script 1 is going to open up the cookies and look for a special cookie. And if special cookie exists and contains a URL for a remote JavaScript file, it's going to fetch that URL and fetch that JavaScript and inject it directly into the page. Now this is, as security folks, the alarms went off, the bells are going on. How can you just randomly inject scripts from the internet into your page? You're asking just for bug crowd payments at this point. But thankfully, the folks at example.com who made script 1, they were really thinking this day. And they were like, you know what? We're going to limit example.com so it only accepts loading scripts that originate from example.com. And so if we set the special cookie to load a script from github.com, that's not going to work because GitHub does not equal example. And then if we set it to load google.com, this is also not going to work. But then what if we find another script, let's say script 2, that also exists on example.com? So this works. And this is really interesting functionality. And then as an attacker, we're kind of stumped. We're like, this is really strange functionality for this page. Why does it process cookies and why does it fetch scripts and inject them into the page? But so as an attacker, we found that we have this limitation where we understand we can fetch scripts, but they can only originate from example.com. And our goal is to indirectly include malicious code into the shopping site. So how can we do this? Well, the whole thing changes if we can find a script that satisfies very specific conditions. 1, it originates from example.com, and 2, it has some kind of vulnerability. And then what happened is this script thankfully existed on example.com. And so, and this satisfies this satisfies the components we need. It's vulnerable and it exists on example.com. Now I'd like to introduce you to the co-star of the show, script 2. Now, script 2 is very similar to script 1. Script 2 is hosted on example.com. Once it loads, it'll open up the cookie jar, and if it sees special cookie, the cookie called special cookie, and there's a string for a remote JavaScript file, it will fetch it and inject it into the page. But what's interesting is, unfortunately, the folks from example.com, they missed the key check in this one. Unlike script 1, script 2 will allow you to load scripts from anywhere on the internet. And so, if we set the special cookie to load script 2, and then tell script 2 to load a script from github.com, that's going to work. And if we set the special cookie to load first we tell script 1, hey, load script 2, and then tell script 2, load google.com, that's also going to work. Y'all can probably see where this is going. If we set the special cookie to load script 2 and then put a malicious script, we'll say evil.com, then this is also going to work. And this is really the big breakthrough. And this is how we're able to indirectly include malicious code into the shopping site. And really, to summarize this, the idea is to load a script with weak security controls to lower the overall security posture of the application and indirectly include malicious code. So let's tie this whole exploit chain together. First, we started on the portal site, and there was a reflected cross-site scripting vector. And then, using this reflected cross-site scripting vector, we set a malicious cookie called special cookie, all using JavaScript, set this malicious cookie to load script 2, and then load evil.com. And then using JavaScript, we redirected the user to the shopping site. Once the user got to the shopping site, it loaded script 1, which is used for analytics, no problem. Thank you, script 1. And then what happens is script 1 is going to go back, and it's going to look at the special cookie, reparse it, and be like, oh, you want me to load script 2? I can do that. Script 2 is from example.com. I have high security controls, no problem. It loads script 2. And then once script 2 gets loaded, it's going to go back, reparse the cookie, and say, oh, you want me to load a script from evil.com? That's fine. I have weak security controls. I can do that. And then that's how script 2 gets loaded, loads evil.com, and then that's how we can indirectly include malicious code into the shopping site, resulting in a DOM-based cross-site scripting vulnerability. All right, now let's talk about some defenses. And I'll kick it off by talking about defense in depth. And defense in depth is really a strategy where you want to build your network or your application like a castle. Maybe previously for a castle, the goal was to defend the keep. And to defend the keep, you had a town, and then some walls, and then a moat. And really the idea is have many layers to delay the advances of attacks. And maybe even once attackers go to your castle and they see all your defenses, they'll be like, oh, no thank you, I don't even want to attack your castle. Now, for us, I don't really see data centers hosted on top of hills with moats and alligators and things. So in this talk, I won't be talking about that. We'll strictly focus on technical controls. So I'm going to take us through 4 key defense in depth approaches that we can think about when securing our applications to prevent clever attacks like this. We'll start off by looking at web application firewalls. Then we'll talk about cookie protections. We'll move on to content security policy, and lastly, secure software development lifecycle. And one thing I want to note, and something we should keep in mind when discussing these, is every single one of these defenses has their own pros and cons. And the idea isn't to find the one perfect solution, it's to properly tune each solution to its max potential, and when layered, they provide a strong and redundant defense story for our application. So let's talk about content security policy. So content security policy is an added layer of security, and this helps us defend against a large amount of web attacks on applications, such as cross-site scripting, clickjacking, code injection, and so on. And this is configured in 4 ways. Content security policy provides us a fetch directive, and a fetch directive allows us to provide an allow list of domains that we want to permit loading scripts from. And so if you think about our example, had we had a content security policy that wasn't fully open, we would be able to only allow list certain domains, such as corp.com and example.com, exclusively excluding evil.com, because that has no place on our application. Next, we have document directives, and document directives help us enforce protections for the DOM. This includes protecting certain elements, such as the base URL. If the base URL gets changed in an injection attack, this can result in clickjacking. The third directive is called the navigation directive. And what navigation directives do is they will allow application developers to restrict locations where forms can be submitted to. And this is important for certain forms such as login pages, credit cards, anything with PII. And if we limit the locations where forms can post information to, this will allow us to prevent against credential harvesting and various phishing attacks. The fourth directive doesn't help us protect really against anything. It's called a reporting directive. And what this does is this gives insight and visibility to application admins to understand where their content security policy is being violated. And so there are multiple examples online of how to configure a reporting for CSP using serverless technology. And this will allow you to analyze violations in your policy. So maybe you can catch all the times that evil.com keeps trying to get loaded. And so content security policy is configured by using the content security policy HTTP header. And most of the basic directives are supported on desktop and mobile browsers. I encourage you to check out the compatibility matrix on the Mozilla Web Docs, and then they go into detail for which directives and which browsers and versions are supported. And if you're curious about the CSP policy on your own application that you manage or on an application that you frequently use, you can use Google's CSP evaluator. It's very comprehensive. And one thing to note is that configuring and maintaining a valid CSP is really hard, especially for very large applications that integrate with multiple third parties. And a study from 2016 from a group at Google analyzed a very large number of web pages. And what they found was 14 out of the 15 of domains commonly allowed loading scripts from unsafe endpoints. And as a consequence, this resulted in around 75% of all policies and 42% of strict policies, they contained at least one insecure host in their allow list. And so you go through all this effort, you do the CSP, and then you find evil.com snuck its way in there. And what's important to note about this is A, we have layers, and B, defense in layers, and B, CSP is an ongoing task. It's not really set it and forget it. As your application evolves and as the industry evolves and what you're using, you need to tune it to make sure it's still correct. And so as an example for how to configure a CSP, let's talk about this one fetch directive. What we can do is we can use default source self, which says the catch-all is my own domain, so example.com. And then we can say only load scripts from trusted.com and any subdomain of trusted.com. That's what the star implies. And then if you want a more complex policy, we can think about this, where we'll only load images. We can load images from anywhere. We can load media from media1 and 2.com. And we can only load scripts from userscripts.example.com. And then the catch-all is anything from example.com, and that's identified by the default source self. And so now you're probably thinking, where could CSP have helped us in our attack example? Well, let's think about it. So CSP would have helped us over here at the bottom. Had we configured a strict CSP to deny loading scripts that we don't permit, this would have denied evil.com from loading. And so had we gone ahead and configured CSP on the shopping site, this would have negated the malicious script from being loaded into the shopping site and prevented us from indirectly including malicious scripts, because in our CSP, we would have only allowed example.com and corp.com. We wouldn't allow evil.com. All right, now let's talk about web application firewalls. So a web application firewall functions as a reverse proxy, and WAFs, they're configured to monitor requests to the server. And the configuration of a WAF is it will sit inline in your application, and so the user traffic will hit the WAF will send it over to your application server. And if we can consider network-based intrusion detection systems as layer 3 defenses, we can think of WAFs as a layer 7 defense. And WAFs are really helpful. They help us protect against a number of web attacks, such as cross-site scripting, SQL injection, and the various OWASP top 10. And what's interesting is WAFs sit in a very strategic place in the network and in your application design, where it's the ingest point to the application. And because it sits right in front there, it can provide a large number of security features for your users. It can provide denial of service protection, rate limiting, and so on, because it will monitor every request that's hitting your application. And similar to any cloud product that anyone's tried to sell everyone, you can deploy it 3 ways: on-prem, cloud, or a hybrid approach. And one really interesting value proposition by WAFs is the managed service offerings. Managed service offerings and auto-updating rule sets can help you have a comprehensive list of rules to defend against. It can provide 0-day vulnerability protection, and also, this is new to me, I actually just learned this, WAFs can also provide exposed credential checks. Because the WAF sits inline in the application and it can do TLS termination, it can actually take a look at the credentials that are sent by the user, and then using their own darknet monitoring or however the company's acquired the credentials, they can check to make sure that your user's credentials haven't been included in a leak. And also, again, WAFs can provide bot detection. And so if we go ahead and we look back at our attack example, where could a WAF have helped us here? Well, had we configured a WAF in front of the shopping site when the reflected cross-site scripting attack was initially set and then redirected the user to the shopping site, the WAF would have caught this and it would have cut the connection and it wouldn't have allowed the redirect to go through. And if the redirect didn't go through, now the shopping site wouldn't have, when it loads, it wouldn't have the malicious special cookie in the user's browser, thereby going ahead and continuing the whole attack. And so that would negate, that wouldn't allow citing the malicious cookie. Script 1 would never load script 2, and then script 2 would never have loaded evil.com, and then that would have prevented the DOM-based cross-site scripting. Just as a note, depending on how corp.com is architected, ideally you should put the WAF in front of all of corp.com and not just your shopping site, but that's another topic. Okay, let's talk about cookie protections. So cookie protections are very relevant for session management. And one of the first attributes I'll cover is the secure attribute. And the secure attribute is set by the server, and when this is set for a cookie, this will only allow cookies to be sent on HTTPS connections. And why this is important is cookies contain sensitive information, and this can prevent against man-in-the-middle attacks, which can take place if there's an HTTPS downgrade attack. And then if the cookie is sent over HTTP, a man-in-the-middle, you can read the cookie. Next, we'll talk about HTTP only. So HTTP only will prevent JavaScript from accessing the cookie using the document.cookie object. And this is very interesting because the first vector, the reflected cross-site scripting vector, actually set the cookie using document.cookie. And what's interesting is using this, This isn't a foolproof protection for cookies because a cross-site scripting attack chained with a valid CSRF attack can in fact disclose the cookie, even if you have the HTTP only flag configured. Next, following on CSRF, let's talk about same site. The same site attribute is used to prevent against cross-site request forgery, and this will help us determine which domains we include the cookie in when we do cross-site requests. Domain and path, these are flags used to define which domains and which paths in the application can process and receive the cookie. And lastly, very important for session management, expire and max age. Depending on their use, this is useful to help determine and enable and disable persistence. So I've talked a lot about cookies, so let's talk some more. Have you ever considered a scenario where you have an application that references cookies using JavaScript, but these cookies aren't set by the user? For me, before seeing this attack, I never thought of this. This is a very strange design pattern to me. However, this is really how this attack happened, is the server didn't set special cookie. The attacker set the special cookie using their first vector, and then the server, and then the application by its own logic always checks special cookie no matter who sets it. And then we think, okay, well, we talked about HTTP only. Would that help us here? Unfortunately, no. Well, actually, no, it would. It would break the application. And it would break the application because the inherent use of the application is it will actually use document.cookie to fetch the content of special cookie and then see if it has a URL for your remote JavaScript file. And so if we use this, it would break the application and prevent the attack, but sometimes when that advice doesn't go too far. And so now we're kind of thinking, what could we have used? We can't use HTTP only. We have very strange functionality for this application. How can we prevent cookie misuse? And to that, I'd like to present content security policy for cookies. This doesn't exist also. And so this directive is obsolete. However, in 2016, the W3C working group published a document that supported CSP cookies. And unfortunately, this didn't make it into CSP3. I think I know why. It kind of encourages poor design patterns, such as the one we see here. But what it did is it defined mechanisms that allow developers to limit the ways in that cookies can be interacted with on their application. And so, for example, if we set the content security policy header and we did cookie scope none, what this would do is this would prevent cookies from being set using the set cookie header or even document.cookie. And this is what we could have used in our example. So also, there's a lot of ifs for this one. If CSP cookies existed, and if we configured them, and if we did them correctly, then it would have blocked the cookie from being set in the initial vector because the payload on the portal site would not, the second part of the payload where it set the cookie wouldn't have gone through because we defined such a tight cookie scope. And so in that case, this would have prevented setting the cookie. Script 1 can't parse it, script 2 also can't parse it, and then evil.com won't make it on the page. So now let's talk about secure software development lifecycle. So secure software development lifecycle has a number of key benefits, and the idea is it's important to do these actions in parallel with normal development work. And this lifecycle is heavily supported by automation. Developers go ahead and provide thousands of commits a day. And what we can do is leverage automation to provide high quality feedback at scale. And as an AppSec team, this is really important because we're able to put the power in the hands of devs and give them the ability to own the end-to-end security for their product. We can give them the tools for automation, we can give them the feedback that they need, and ideally provide them the feedback for these security tools in the same place that they're actually developing code, so it's easier for them. And what's awesome about this is this helps developers spend more time working on features that customers value and things they want to work on as well. And so this is really characterized by the Shift Left initiative. And again, the idea, instead of appending secure software development lifecycle to the end of the traditional SDLC, we go ahead and run it, we move it down and run them in parallel. And so going into each of these stages, let's think about the requirement stage. In this stage, developers are thinking about what does their application need, what kind of information should it accept, and what requirements are it trying to fill. And here, this is a great time for us to identify key security functionality. Are we collecting user data in this feature? Are we collecting PII? Are we doing any cryptography? And so this allows us to perform a risk assessment very early on in the application. Next, at the design stage, this is where developers have the requirements, they know what they need and how to get there, and now they're wondering how to put the pieces together. And during the design stage, at least for cloud architecture, these stages are, the design is still very new, it's very fresh and malleable. This is a great time to think about threat modeling and do design reviews because the architecture can still be changed. It's not expensive to change, sometimes it's expensive, but maybe not too expensive to change things early on in the process. And so what we can do is identify architecture concerns, and we can provide mitigations to provide security for the rest of the process. And third, during the development stage, this is where we can heavily lean on our SAST and software composition analysis tools, where we leverage automation to provide feedback to developers and detect against insecure coding patterns and so on. And then we have, during the testing stage, hopefully developers run a unit test for their application. And when they are, this is a great time to consider critical feature tests. And so let's say the project is secure file storage. And we have this rule for secure file storage where user 1 cannot access files of user 2. This is a traditional unit test. However, security has a key investment in this specific test case because it validates the security posture for the application. And so this is an example of a critical security test, critical feature test that security has interest in at this stage. And lastly, we have the deployment stage. And during this stage, we can think about patching new vulnerabilities, maintaining the application, and potentially doing routine assessments based on your organization's needs or compliance requirements. And so let's go back to our example. Where could secure software development lifecycle have helped us here? Well, to be honest, it could have helped everywhere, but we got to focus. So we will focus on the applications that we control. Had the portal site gone through the entire secure software development lifecycle, we would have been able to determine that there was a reflected cross-site scripting vulnerability in the page. It would have gone through design review, and it also would have gone through our threat model, and the SaaS tools would have caught this. And then if we look over on the right for the shopping site, had the shopping site also gone through this, a part of the design review and threat model is taking a look at what the third-party applications are. And during this instance, we would have been able to take a closer look at example.com and understand their functionality and how it works. And this is how we can make sure that the strange third-party advertising scripts don't make their way into our application. Or if they do, we lock them down real hard. And so more or less, this would negate the reflected cross-site scripting vector and the DOM-based cross-site scripting vector, which means that the entire exploit chain would be mitigated. And so now let's think, what does our defense in depth story look like for all of corp.com? We talked a lot about these attacks. We talked a lot about these defenses. Let's put it all together. Okay, so let's start with CSP. What if we configured the CSP at the bottom and we used a fetch directive to only permit loading scripts from example.com and corp.com? This would have prevented loading the script from evil.com. And then what if we used the WAF and we positioned the WAF in line with the application for the shopping site? The WAF would have detected the reflected cross-site scripting payload when the user was redirected to the shopping site, and it would have cut that connection. And then lastly, what if we use the secure software development lifecycle and we put the portal and the shopping site through all of the rigor and steps that we've all discussed? And so at this point, we can pat ourselves on the back and rest easy because this is how we can prevent and defend against multi-step cross-site scripting attacks that show up in our nightmares. Thank you. Thanks. And I'd like to give a special thanks to the Meraki security group, particularly my manager, Natalia Krecker, and tech lead, Brett Bergen. Any questions?
All right, over here. Here you go.
It's clearly an anti-pattern to load a script from a cookie. So how can you detect that in, say, static analysis or dynamic analysis to catch like other teams trying to do that?
Yeah, that's a great question. To paraphrase, the question was, it's an anti-pattern to load a script from a cookie, and so how can this be detected? And how this can be detected is the way the script is loaded. It's using a JavaScript method to fetch a certain URL, and usually this can be picked up, that specific fetch call, and also I haven't tested this, but I assume JavaScript referencing document.cookie should also throw a flag. Maybe not a red one, maybe a yellow one. But if you chain that with the flag for the HTTP call to the other script, that, fingers crossed, will get picked up. Yeah. Thank you. Any other questions?
All right. Can we get another round of applause for Omar? Thank you.